Yeah, let's do that.
Using your slide.
Okay. So here's the goal for this part. The idea is this, that a lot of researchers are given a big production MD code to use. Maybe this includes you, something like LAMPS or VASP or one of the other codes. And these tools are pretty complex. And because of that, we often treat it as a black box. And I know for a lot of students that I've taught that this can be fairly intimidating. As one graduate student here at MSU told me, he says, I'm really worried to use this very complicated black box because I'm afraid I'm going to misuse it. And one of the things that he told me was really useful for him was to have the world's tiniest MD code so that he could just play with it and build up his confidence on what he was doing before he used a production code, like in his case, he was using LAMPS. So that's the idea. So what I did is I wrote an MD code that's just a few lines long, and it's in the Jupyter notebook, which I sent to you, and you can have it, or I have little snippets of the code in my slides. And what I want to do, since this is hands-on, is I want this to be very interactive, and I want you to be the ones who are talking, not me. So that's what we're going to do is I'm going to basically, which can like have a conversation about how this code works to help you build up your intuition for how to use an MD code. So in that spirit, maybe we can start, and some of you, the students, can tell me what codes you have used before and what codes you're using now and what your level of experience is.
Hello, Michael.
Yes.
Yeah, this is Mitul.
Hi.
Yeah, hi. I am using the LAMPS at presently, and I am new to this code, so I don't have much experience of LAMPS, but still I'm using it for the radiation card-state simulation in diamond detector, basically.
Ah, okay.
Yeah.
Awesome.
So I'm using the LAMPS actually.
Great. Thank you. Thank you for that. Anybody else?
Sir, my name is Chirag. I'm from India, Gujarat. I'm also working on warm-dense plasma, and yes, and I've been following your work for 2 years, and I also use LAMPS to generate paired potentials.
Oh, fantastic. Fantastic. Good. Okay. Anybody else want to say what they're working on, or? Okay, well, let's continue with that. So we have 2 LAMPS users.
We were also using GROMAX to simulate the pH instability in water. But we are just learning.
Oh, excellent. Excellent. What potentials are you using? Do you know which water potentials you're using?
Yeah, we are using LJ potential right now.
LJ, okay, perfect.
Right.
Great, so we have 3 people. All right, GROMAX and LAMPS. All right, so let's go. So the code I gave you is a little 2D MD code. It's super fast. You can play with it, build your intuition. But what we can use today, even if you want to just use the code you're using, you don't have to play with this code, but we can talk through it. I'm curious to see how you guys make your decisions. So let's start with this. So this is a little part of the code I sent, but the code itself doesn't really matter. Really, what is the questions? So in this code, let's look at the first question here. If you look at this code, what assumptions have been made? So when you run your code, you make some assumption. Can you think here what assumptions have been made? Like what information is not being provided?
The units of time.
Units of time, yep, perfect. Anything else?
Initial velocity, somebody said.
Initial velocities. Yeah, so that's what this line is doing, which we will get to. That's a good point. We'll get to that. We have to initialize the positions and the velocities. We don't know what the units are. Can you think of anything else?
Yeah, we do not know the volume, the
The
dimensions.
volume. Exactly. We don't know the dimensions. So we can't set the density. That's right.
Yeah.
So in the code I gave you, it assumes that the box is 1 by 1. So that's how you get the volume, but that's good. So let's go to the next one. Can you think of any other steps that you might want to include here?
Boundary conditions.
Boundary conditions, good. So this part of the simulation right here is simply just setting it up. So I'm setting up the number of time steps. I give you the DT, number of particles. I don't know the volume, and I initialize the particles. That's probably good, don't you think? So let me ask you this, especially those that are using GrowMax and lamps. How do you guys choose your time step?
We generally use some prescribed time steps. I think
Can you say that again? Which time step?
I'm choosing time step from the literature I'm referring, but it is I need to learn how to take the time step.
Okay. I think somebody's in traffic.
Yeah, we have muted him now. Yes.
Okay. So I think this is one of the most important issues that I've seen with people who are learning MD is how to choose the time step. And here I set it to some number. As you correctly pointed out, there's no units, so I don't know if this is a good time step or not. And here's the way that I typically think about choosing the time step. I think of it in terms of 3 different ways. And they all come down to characteristic time scales that are important in the problem. So you said that you use, for example, LJ potential, right?
Right.
So if you look at the LJ potential, let me see if I could switch back and forth. If I take a potential like this, like a LJ type potential, which is blue, there's an oscillation frequency in this well because it's like a harmonic oscillator. So if you're really cold and the particles are stuck to each other, then you know they're oscillating in this potential. And guess what? Because this is like a harmonic oscillator, you know the frequency. So you pick your time step to be like something like 1/10 of the frequency of the oscillator of this well. Does that make sense?
Right, right.
That's one way. So if you know something about your energy scale and you know something about the shape of your potential, you can choose an intelligent time step. And once you have that intelligent time step, you can check your energy to see if it's conserved. If it is, you probably have a good time step. Let's go to method number 2. Method number 2 is when you have a system that has a collective mode. Like one person's doing warm dense plasmas. plasmas are very well known for their collective modes. You have ion acoustic waves, plasma waves, lots of different waves. Those waves have very specific frequencies. So even if the potential doesn't have a well, like a Coulomb potential, the Coulomb particles will set up a collective mode with a specific frequency. You can use that frequency to guide you what your time step is. So you can use the shape of the potential, or you can use some sort of collective phenomenon that you know is happening in the system. That's method number 2. The third method for choosing the time step is collisions. Sometimes you just have, like, imagine if you have hard spheres. There's no well, they're just flying and hitting each other. They're not particularly collective, but you know the frequency at which they collide with each other. So if you can estimate a collision frequency and resolve it by making delta t 1/10 of that time, you're going to resolve the collisions. So you have basically in MD, you have usually one of 3 timescales set by the shape of the potential, collective modes in the many body system, or collision times. That makes sense?
Yes.
Does anybody have any other way that they like to choose the time step that's different from those 3?
Yeah, one I know, one we know when we do some other simulation, the current condition. So this will guarantee that current condition is satisfied. That my
Okay.
simulation, my simulation speed should be faster than any physical speed present in the system.
Gotcha. Yeah, good. Does anybody else have any other rule that they use? Okay, let's move on then. So when you guys do your simulations, how do you choose the number of particles? How would you go about making that decision?
With the help of the density of the liquid or material we are simulating.
Right. So let's suppose I do that. Suppose if I choose the density, I can choose a really small cell size. So I have a fixed density, but I have a very few number of particles. I just make
Right.
my volume really tiny. But probably you don't do that because it's too small, right?
Right.
So probably what you do, I'm guessing, is most people choose the number of particles to be absolutely as large as possible to get the best statistics.
Right. Yes.
And basically limited by computation time.
Right. So is it true that more number of particles will come to the equilibrium faster?
No, it's pretty much independent of that in terms of equilibration.
Okay.
Yeah, equilibration is always very slow. People do research on how to speed up the equilibration process because sometimes it's the longest part of the simulation. But
Right.
okay,
Yes.
let's keep going. Okay, now what we have is we've set up our simulation. We know how many time steps. We need to go out a certain length based on the physics we're looking at, whatever it is. We have a time step that we've intelligently chosen. We picked as many particles as we can. Now we're going to initialize the particles. Okay, so we're going to go here. And this is like a very crude way to initialize particles. So I'll give you a second to look at this code. It's literally one line. Okay, so you probably looked at it. It's only one line. So what assumptions have been made about where the particles are placed? So this is putting the X position, Y position, VX, VY, or PX, PY. So what assumptions have been made about where the particles have been placed in physical space? Do you guys know you know this notation in Python?
Yeah, the particle have been placed between 0 and 1.
Yep. And how have they been placed? Do you know this particular random number versus this one?
Yeah, one is the uniform random number, I guess.
Right, exactly. So can you think of a problem with that? Would you do that? Have you ever done that?
Yeah, maybe a lattice.
Exactly. So when would you use random versus a lattice? Has anybody ever used a lattice versus random?
In case of gases, probably we will use random, the Gaussian one.
Yeah, so here's what happens. If you have a lot of particles, if you do it randomly and you have a lot of particles, you will eventually get particles that land almost right on top of each other. So typically in MD code, if you're using lamps or GROMACS, probably what it's doing is it's using what's called a rejection method. And it's putting the particles down randomly, but if it gets too close, it gets a new random number. Because you never want the particles to be too close because they will fly apart at very high speed. So even though in the code I gave you, I used random and random, this in general is not a very good idea. Especially if you have a large number of particles, eventually they're going to get really close. So your idea is great, right? If you put a lattice and you put them on a grid, it basically guarantees that they're not going to land on top of each other. But sometimes there are cases where you don't want to use a lattice. And it's what you said earlier. If you have, it might take a long time to equilibrate. If you start in a lattice and you're doing something like a disordered system, like a warm dense plasma, the equilibration time could be very long. So typically, if you write a code or you're using a code, the way you put them down in physical space can be important. It can be important because it could cause problems, or it could be important because it could take a long time to equilibrate. Okay. Okay, so let's keep moving. So can you tell the shape of the simulation cell? Just by looking at this, can you tell what the shape of the simulation cell is?
Square.
It's square, right? With from 0 to 1, 0 to 1. So now we know our volume. Okay, now what can you say about the initial momenta? How am I initializing the velocities?
So all the x component, yeah. Gaussian distribution. Somebody said Gaussian distribution.
That's exactly right. Randin is a normal distribution, random normal. A normal distribution is a Gaussian. So I'm basically assuming the particles are in thermodynamic equilibrium initially. You don't have to do that, but it's a very typical thing is to assume, at least before I do equilibration, that I'm in equilibrium. That's exactly right. Okay, what if I want to change the initial temperature? What would I do?
Yeah, somebody said thermostat. You can use the thermostat.
But this is just the initial temperature.
Yeah, initial. We need to multiply by different factor instead of 0.1.
Exactly. That's what this 0.1 is doing, is it's basically setting the temperature. That's exactly right. So this is like this, it's only one line, but it's like the simplest code, but it teaches us a lot about the way we think about what we do before we ever even get to our integrator, which is how to put the particles down in phase space without causing problems, how to control the temperature, how to make it start in equilibrium. All of these ideas are embodied in this one line. And so probably when you're using Gromax or lamps, you're making similar decisions in your input file, but this is what it's doing inside, something like this. So, okay, let's keep on going. Okay. One of the things that we haven't talked about in the main lecture was boundary condition. So maybe before I talk about this, maybe those of you who are using Gromax and lamps, what sort of boundary conditions do you typically use?
I use periodic boundary condition.
Periodic. Okay, good. Anybody else? Was that also periodic?
Yeah, another answer, periodic. I used not in particle simulation, but in other simulation, I used absorbing boundary conditions also.
Absorbing. Okay. Great. Okay. So this picture right here is an example of three-dimensional periodic boundary condition. So what it tells me, I have right here, what types of systems does this apply to? So when I hear that a lot of you are using periodic boundary conditions, what it tells me is you're doing bulk systems. You're trying to mimic a large piece of homogeneous material, right? So what do you do if you're doing that? Periodic boundary conditions are great. How do you compute the force on each particle in periodic boundary conditions? Like, what if I wanted to compute the force on this particle? What do I do? How would I go about getting the force on this guy?
Negative gradient of potential, but he is asking the particle which is exactly on the boundary. What will be the force on that particle?
Do I get minus the gradient of the potential from this one? And this one? And this one?
No, towards the end, I think it will be infinite. No.
Exactly. It will be infinite, because if it's periodic, this goes on forever.
Right.
So when you use periodic boundary conditions, you can't just simply sum up all of the forces. And that gets to this question here. How many force calculations are there? If I do a naive force calculation of every particle with every neighbor, that's going to scale like n squared. And if I have periodic boundary conditions, n is going to infinity. So the number of force calculations is infinity squared. I'm pretty sure none of these codes do that. So what do they do? Here's what most of them do. What they usually do, because we can't compute forces out to infinity, what we typically do is we choose a cutoff radius. Remember, I mentioned this in the main lecture, that because you can't compute forces out to infinity, at some point you simply have to stop. And the place that you stop is called the cutoff radius. And this is the point on this dashed line where I showed you where the potential has that glitch. And this is where the force goes to infinity. Okay. So there's three ways that I know of choosing the cutoff radius. One of the most common ones, which is a little bit naive, is what's in the title. It's called the minimum image convention. And in the minimum image convention, you choose the cutoff radius to be half the box length. So basically this particle right here, the red one, you can go L over 2 in this direction, L over 2 in this direction, L over 2 in this direction, and L over 2 in this direction. And you draw a circle between those points. That's called the minimum image convention. And you see that used a lot in MD. It's kind of a nice, simple way to do it because it just basically says, if I have periodic boundary conditions, I don't really trust what's going on over here. It's a nice boundary condition, but it's not real. I mean, it's not really an exact replica. So I don't want to really trust it. So I only want to go a distance of L over 2, L over 2. And that's the minimum image convention. So do you guys use this and do you think it's a good idea? What do you guys use for your cutoffs?
This is a good idea, safe idea, but I think we will have to do more and more computation with this.
Yeah, that's exactly right. What if you have a large number of particles and your LJ potential goes to 0 very quickly? This would be very safe, but you would do a lot of extra calculations that are almost 0, right?
Right.
The other limit is the opposite one, which is suppose you're doing a code that is really expensive, like VASP. And in this cell, you only have like 50 particles. And when people run VASP, they make the cutoff be all the way out here, like this big. They make it go outside into the neighboring cells. So they have to sum over like 27 extra cells. So this is one of the reasons that VASP is very expensive, is you have to go really far outside the main cell, above the minimum image convention. Whereas for a fast LJ pair potential, you go below the minimum image convention. But if you don't know, then the minimum image, as you said, is kind of safe. Does that all make sense?
Yes, sir.
Okay. So let's look at this code here. This piece of the code implements the periodic boundary conditions, and it uses the minimum image convention. Okay, so I'll let you look at this code for a second, and then we can talk about what it's doing. Okay, that's probably a good amount of time. So let me walk you through it. Does it make sense to everybody? So this top line is a little bit, excuse me?
Guruji, could you please mute your mic?
Is somebody going to ask a question?
No, so somebody made a remark, I guess.
Guruji,
Okay.
just wait. Guruji, could you please mute your mic because there is an echo problem. Okay, thanks.
That's nice. Okay, so let me continue. So if you look at line 10, what this line is doing is basically I have an example up here. It computes basically like a distance meter. I think now someone's might be in the wind. Okay. This first line 10 here basically computes a matrix of distances, and these are all the x distances. So basically line 10 computes the x distances between all of the pairs of particles. So a very fast Pythonic way to do it using NumPy. And then once I have a distance matrix, I can use a mask to figure out how many of the distances are greater than L over 2, and how many of them are to the left of me that are L over 2. And that's implementing the minimum image convention. That's what I have in my code, which is a safe guess. And then what I do is if the particle is too far to the right, I flip it over to the other side. If it's too far to the left, I flip it to the opposite side. And same for the Y value. So let me walk you through that. Suppose this is the particle I'm looking at, this blue one here where my mouse is, and I'm computing the force due to the red one. Well, the red one is more than L over 2 away from me. So when I compute the distance from the blue to the red, it's going to be outside the minimum image convention because it's almost L away from me, definitely more than L over 2. So because it's more than L over 2, I'm going to subtract the box size from this guy. And if I subtract the box size from this guy, it's equivalent to computing the force of its periodic neighbor right here, which is very close to this one in terms of X. Now you might say, well, this one is closer to this one than this one in X, but it's greater than L over 2 in Y, and that is true. So what would I do? I would have to take it and also add the box size to it, and then what I would get is I would end up getting that, that the force on this guy due to this particle is actually computed using this image, because this is the closest image of this particle. And that's what minimum image is doing, is if it's too far away, it just flips it so that it's close. And that is equivalent to just basically drawing a circle around the particle. If you see this, if I draw a circle around it, this particle ends up being this particle. So there's different ways of interpreting it, and it's a little bit tricky to code it up. You have to kind of get the logic. But this is what most codes are doing. They're either doing minimum image like this, or they have some sort of an if statement that's doing a cutoff radius. And there's very sophisticated ways of doing this because it can take a code and change it from order n squared to being order n, which is a lot faster. And it also makes it easier to parallelize. So these are all very important considerations. Even if it seems kind of tedious, it can change your code a lot. So if you're changing the input values in LAMPS or GROMACS, you want to make sure that you know which decision it's making. Okay, once it's done all that flipping of particles around, you get the distances, you get all the forces, and then this subroutine returns the force on the particle in the X direction and the force in the Y direction using all of the particles that are in the right place according to the cutoff radius and the minimum image convention. It's amazing. All that complexity goes in just to get those forces. Okay, let's keep going. Now that we have the forces, we can finally do an update. So here's a question here. Is Newton's law being used here? And how is it being used and what does it do? Can you figure it out? Do you guys remember what Newton's third law is? Newton's third law is for every force, there's an equal and opposite force. Why would that be important in molecular dynamics? Any ideas?
Yeah, conservation of momentum.
Exactly. It's enforcing conservation of momentum. And what's interesting is you can enforce conservation of momentum exactly, because what Newton's third law says is Fij equals minus Fji. So if I calculate, if I'm writing a code, and this is in all the major MD codes, if I calculate Fij, what am I going to do? I'm going to save it. And then later, when I need Fji, I go grab it and just put a minus sign in front of it. So not only do I guarantee that momentum will be exactly conserved because I'm literally using the same number, there's another benefit of this is if I write a naive code, and this code that I'm showing you here is very naive, it takes my code from n squared to n squared divided by 2. So by using Newton's third law, I literally make my MD code twice as fast. So every MD code is going to use this trick because it's like a free factor of 2. Okay, so Newton's third law is always being used in every MD code. And one of the things you can do is you can print it out. Like next time you run LAMPS or GROMACS or whatever code you're using, next time you run it, plot the total momentum and see what you get. Now, what you might think you would get, I've done this experiment, and what you might think you would get is that the momentum is conserved perfectly. It's just a perfectly flat line, because wherever I have Fij, I use it where I have Fji every time. So it's should be perfectly flat. But in fact, for numerical reasons inside the computer, it's not perfect. And you see little fluctuations around the machine precision. But it's not constant, but it's at machine. There's little round off errors at machine precision that you can look at. Of course, nobody cares about that. I'm only telling you because it's sort of interesting, and you can look at it and confirm that that's what's happening. So, okay. So can you tell from this code, I claim up here in the comment that I'm using the Euler-Kromer method. Can you verify for sure? Can you tell whether or not I'm actually doing that correctly? Is it obvious to you that that's what I'm using?
The last 2 lines to update the positions.
That's right. So I compute all the momenta or velocities first, and then I use those values to update my positions. So I use updated momenta to get my positions. That's Euler-Kromer, and that's the one that gave me that perfect circle. Really beautiful. So here's my question for you. Would you use this integrator? So when you guys do your simulations of water and warm dense plasmas, what do you use? What integrator do you guys usually pick? I'm curious.
We use Verlet, velocity Verlet.
You use velocity Verlet? Okay. Does everybody use velocity Verlet?
Same.
Same? Okay. Yeah, it's pretty much a classic. It's so good that almost nobody uses anything else. So I'm not surprised that that's what you use. So, okay. So let's keep on going. The second part of this. So here I know the forces, I update the positions, I update the velocities. Sorry. I know the forces, I update the velocities or momentum, then I update the positions. That's down here. Let me try my laser pointer. Now I get to the second half of this routine, and I have to handle the boundary conditions. Why do I need to handle the boundary conditions again? Didn't I just handle the boundary conditions in the PBC function when I was doing minimum image convention? Why do I need to do it again? Okay, I'll tell you why. The reason is the reason you have to deal with boundary conditions 2 times is the first time you use the boundary condition, let's suppose I'm looking at the force on this particle, this red particle. The first time I need to use the boundary condition is because my cutoff radius is likely to go into neighboring cells. So I need to keep track of, as I move around in this volume, in this case, it's a circle, but usually it's a sphere. As I move around in this sphere, sometimes I'm in this cell, sometimes I'm in this cell, sometimes I'm in this cell. And if I'm using minimum image, I need to make sure which particles I'm looking at. That's to get the force. Once I have the force, I get the momentum. Once I have the momentum, I update the position. Now, what happens if I update the position and this particle ends up over here? That's bad because it left my cell. So the second implementation of boundary condition is after the particle moves, like let's take this red one right here. When this one moved, it left the cell. And now it's out in the middle of nowhere. It's not in my cell anymore. So the second point I have to treat the boundary condition is I have to check after I've done all my forces and integrator, did my particle leave the cell? If so, I need to bring it back in. So this particle right here is bringing it back in because over here it left. So I have to check the boundary condition to get my forces right. And then after I move my particles, I have to make sure that they didn't leave the box. And if they left the box, I need to wrap them around and put them in on the other side. So that's what your code is doing. And that's what this boundary condition is doing, is if it's greater than 1, that means it left here, put it back in. If it's less than 0, that means it left this way. If it's greater than 1, it left on the top. And if y is less than 0, it left through the bottom. And of course, in 3D, you would have more of these. This is just a 2D version. So that's why we have to check the boundary conditions to make sure our particles are not leaving us. That's really where the periodic wrapping is coming in. Okay, now here is a really tricky question. I'll see if anybody can figure this out. Hopefully your coding is good enough. If I took these white lines out and uncommented these lines, comment this white one out, uncomment the green one, comment out the white one, uncomment the green one, same thing here. Can anybody figure out what that does? What would that do?
So they should give us a similar effect, because then we are saying that particle is getting reflected at the boundaries.
Reflected?
Yes.
It's exactly right. It's exactly right. So the white ones are doing periodic wrapping. So if it goes out the top, it comes back in the bottom. But if I comment that out and I use the green one, it's not changing the position, it's changing the momentum. So if it goes out the top, out the right side, it takes the momentum in that direction and it flips it. So another way to say this is the white lines are periodic boundary condition and the commented green lines are reflecting boundary conditions. And obviously, they're going to give you slightly different dynamics. But that's a nice way to write a code, is to make it so that it can do multiple types of boundary conditions. So you got it perfectly. Good job.
So which one will be the better? I mean, periodic or reflecting?
I think it really depends on what problem you're working on. I think there are problems for which the reflecting is really what's happening. And if that's what's really happening in your system, you probably want to use them. However, most of us, I think, are simulating bulk systems. And when you have a bulk system, what you want is when a particle gets near a wall, you want it to think that there's material on the other side of the wall. So if I want to mimic a bulk system, when a particle comes near the wall, it should think that there's particles over there. And that's what periodic boundary conditions is doing. So if you go over here, as any, like when this red particle here that I'm circling approaches this wall, what does it see? It sees all of these particles in its minimum image. It thinks it's inside of a bulk system. And in that case, if you think that your system is a bulk system, definitely want to use periodic boundary conditions. If this particle were approaching this wall and it saw nothing until it hit the wall and then it bounced back, that would be very different from a bulk system, but it might correspond to like a bunch of particles that are trapped in a well. That might be the right thing to do for that case.
Okay.
There's a lot of options. Have you noticed that? This is why a lot of the decisions you have to make yourself because it's so problem dependent. Okay. And then finally, what this does is it does some visualization. The visualization I did in this little Jupyter notebook is obviously extremely crude, but you guys probably are using visualization tools, I'm guessing, like the one in the lower right here is VMD. What visualization tools do you use? This is Ovito. This is the one we typically use here is Ovito. We have a license for this. What do you guys use for your visualization?
I use Ovito.
Ovito? Okay. Do you have a license for it or are you using the earlier version?
No, not licensed one.
Not licensed. Okay. They recently, it used to be free and now they're starting to charge.
Yes.
But we really like it. And we've had really good success that whenever we have a question or an issue, we contact them and they respond immediately. They are extremely, extremely helpful. So we continue to use them. So, okay, the one I have in my notebook is obviously very simple compared to these, so I won't even show it. But that's the final step is once you're done, you visualize it and you get physical information. So that's it. The only thing I wanted to say before I finish is if you kind of like having a code, this is, by the way, an advertisement. If you like having a code that you can play with, and a lot of people like to use Python because it's easy to code in. One of the things that we've developed here in my research group is this Python. It's a pure Python MD code called Sarcus. Maybe all of you know what that means. And it is open source. It's free. You can download it from GitHub. We try to make extremely good documentation and code examples and Jupyter notebooks. You can run it directly from a Jupyter notebook. It's really convenient to learn and run, lots of examples. And we have a paper on it. A little bit of an advertisement, but I just wanted you to know about it in case you want a code that you can just rip apart and play with it and change it. You can read the code yourself. It's easy because it's all Python. And we're currently, Luciano is my postdoc, and we're developing it, and Luciano loves helping people. So if you want to try it out, you can try it out. Obviously it's not currently as well developed as the big codes like Gromax and LAMPS that have been around for a really long time. But it's a really nice code for like there's a group in Germany that's using it, and they like it because it's easy for them to go in and make changes and they put in their own boundary conditions, they put in their own force laws, they do all that kind of stuff, and they find it to be pretty convenient. So I just wanted you guys to know that it exists if you ever are looking for an MD code that satisfies those sort of needs. And then finally, that's it for me. If you want any information, feel free to contact me. I can send you these slides or whatever you need. And if you have any questions now, I'm happy to take any questions you have.
Yes, time for questions. People online can unmute themselves and ask the questions, and people in the hall can raise their hands. Yes. Chirag has some questions.
Hello, sir. Can you hear me?
I sure can.
Sir, I'm using a screen Yukawa potential with strong range repulsion. So in that case, should I use evolved method? Is it appropriate in that case?
Oh, wow. That's a really tough question there. The answer is very complicated. Let
Okay.
me show you. We wrote a paper on this. This is why I say it's complicated. It's an interesting question. So we wrote this paper. Can you see this?
Yes, yes, sir.
Okay. So we wrote this paper to answer this question. So we do screened Coulomb interactions, which is Yukawa.
Yes.
And we asked the question, should you use Ewald or not?
Okay, sir.
And we wouldn't have published a paper if it weren't for the fact that the answer is very interesting. So what we found is if the screening is very strong, so if you know kappa in the Yukawa literature, if kappa
Okay,
is
sir.
large, the screening is strong, you definitely should use a neighbor list.
Okay, sir.
But if kappa becomes small enough and it approaches the one component plasma limit, it becomes advantageous to use Ewald.
Okay. Okay, sir.
I think the
Thank you.
problem that you'll run into, let me just say one more thing about that. The problem that you'll run into is that most codes, when they implement Ewald, they only do it for kappa equals 0. So in practice, if you're simulating a Yukawa system for a really small kappa and you think you want to use Ewald, the problem is your code probably doesn't have the generalized Ewald decomposition in it. So you have to check. Most codes that we're aware of still use the Ewald decomposition only for pure Coulomb.
Okay, sir.
But yeah, that's a great question.
Thank you. I have one more question.
Sure.
What happens sometimes the properties depends on the box sizes, or I say the number of particles. So do we have to test it for each and every property, or is there any thing that you can tell me?
Yeah, that's a good question. We looked at this here. That was sort of this plot here.
Yes, exactly. Diffusion coefficient.
Yeah, so I don't know about you, but whenever I do simulations, I always start off when I'm just testing things and trying to figure out what my time step is and trying to figure out all these things. I always do a bunch of runs with a small number of particles. And then as I figure out things, I start to raise the number of particles a little bit. And I kind of end up making plots like this kind of indirectly. I mean, this plot that you're seeing here was made very deliberately because we really wanted to know what the finite size effects are. But what I end up doing is I kind of end up doing plots like this kind of informally while I'm testing the code. And I think you kind of always have to do that unless you have an intuition. Like, for example, if you have 10,000 particles, you know you're safe. There's probably no reason to check. If you're down in the 100 level, you probably need to check.
Oh. Thank you, sir.
Yep.
Can I ask one more question?
Of course, many as you want.
Sir, we are also planning to do quantum molecular dynamics and then use it to fit with machine learning. So,
Great.
In that case, what anything that you can suggest me that I should take care of? I mean, while running a quantum molecular dynamics simulation, either about a step size or maybe a box size or something, because it's a very costly calculation.
Yeah, that's a good point. So if you're going, like in this case, that's what we did. We ran VASP And one of the things we did is we spent a lot of time thinking very carefully about the VASP runs, doing little tests to get the time step, making sure that it was equilibrated using previous data. So the equilibration was shorter. We did a lot of discussing with Ray and Luke just to make sure that we would minimize all of our effort. And then that allowed us to do the shortest runs. Each run ended up being about 2 weeks, even though we tried to optimize it. And then we have these giant files, and then we did the machine learning, we got the potentials, and we made these curves. Let me ask you this: how are you doing the machine learning? What are you using? Are you writing your own or using some package? What are you using?
Yeah, I think that I either I will use using a PyTorch or I using a Julia and Flux.
Okay.
I think.
So it's going to be a neural network.
Yes, I will use neural net.
Okay, great. Well, that's great. I look forward to seeing that.
Thank you.
Thank you.
Thank you.
Yes, are there other questions from people online? Yeah, in case there are no more questions, let us thank Professor Murillo for those wonderful sessions. And you all will agree that we could have not find anybody better than him to teach us these basics. And I also want to mention here that it is a late midnight for him. It should be around
3:30 in the morning.
3:30 in the morning. So that's the kind of passion he shares, and he's really doing to help all of us. So highly appreciated, sir. And we really thank you for the time you have taken and the efforts you have taken to put this session together. We will definitely love to get back to you in future if we organize things related to molecular dynamics.
Well, thank you for having me. I appreciate it. It was wonderful talking to you guys. Thanks for the opportunity.
Thank you, sir. I think now you can go to sleep for whatever is left to you.
Thank you, Murillo.
Whatever's left.
Thank you, Murillo.
All right. Have a great rest of your workshop.
Thank you so much. Thank you. So bye-bye, sir.